All right, I'm going to say something about magnetic monopoles now. So I have talked about this before, but um, if you remember, so this is going to be basically a completion of the discussion in a way. So what are magnetic monopoles? These are essentially magnetic charges. So a north, for example, is going to be the source of the magnetic field. So as a result, if there's a north pole, all the magnetic field lines start from there and then go to infinity or whatever. So the south pole is basically just the opposite, so the magnetic field lines end up there. So these are like the positive and negative charges, but for the magnetic field, so that's a positive charge, and this is negative charge. How do we say this actually? Basically we identify these poles by just looking at a magnet. So in a magnet, of course, we have this north pole and a south pole, and if you just look at the magnetic fields produced by the magnet outside, it appears that the magnetic field lines are starting from the north pole and then it ends up in the south pole. You can also do things like, for example, if you just compute the force between two magnets, let's say, you can treat these poles as if they are point charges and then compute that force. So that's also entirely possible. So as a result, there is some kind of a parallel between the electric charges that produce electric fields and the magnetic charges. Unfortunately, they don't exist. So we know that, for example, if you just try to separate these poles by just cutting the magnet into two, we know that this is going to produce new poles in here. So as a result, somehow we cannot isolate the poles. So somehow north and the south somehow should appear together. So we know the reason why this happens, because we know that, of course, it's just our imagination in here that there appears to be a north pole and a south pole. We know that they don't exist. So inside the magnetic field somehow continues. So as a result, the magnetic field lines do not start from here. They are actually, just as we have said before, they just continue. Why this is so? Again, we know that this north and the south poles are actually produced by the currents inside, electric currents inside atoms. And from that perspective, if you remember, we have defined something called the magnetic dipole moment. And in that case, it appears that at least this side of this current loop should be denoted as north, and the other side should be denoted as south. And as a result, I mean, since this is not some kind of a particle, it's just a current loop, I cannot divide this into two. So as a result, I cannot separate this north from the south, right? We know that somehow it appears that there is some kind of a reasonable magnetic charges in there called north and south, but there aren't actually. So we know that the electric currents actually produce these. But I have said that somehow the physics, the laws of electromagnetism is consistent with the existence of magnetic monopoles. So there might be some particles. We don't know whether such particles exist or not, so we have never met them. But there might be some particles that they might have these magnetic charges. So perhaps such a particle will be just north, where the south will be nowhere around. All right, so it is in fact possible. Equations tells us that this is the case, and I'm just going to explain how this somehow conforms with the Maxwell's equation. So let's remember these equations. So we have the Gauss law and the Gauss law for the magnetic fields, Gauss law for electric and magnetic fields, if you remember. The asymmetry is in there basically. For the electric fields, we say that there are electric charges, but for magnetic fields, we say that there are no magnetic charges. So that's basically the statement. Within that statement, of course, somehow I'm excluding the possibility that the magnetic charges do not exist. They may exist actually. So we are excluding that possibility. So this is the claim that the magnetic monopoles do not exist. But I can change the equation and add something to the right-hand side that has something to do with the charge of the magnetic charge in here. So I just add a magnetic charge term in that to the right hand side, in that case, perhaps I'm going to get the correct equation for the magnetic monopole. So I'm going to do that, but let's also note this. There's also electric charge current in this equation. So let's just remember the last two equations. So these are actually line integrals of the electric and magnetic fields, and on the right hand side we have some flux, time derivative of fluxes of fields over this enclosed surfaces. In any case, there's also an imbalance in here. So the electric current somehow appears in that equation, but nothing appears in this equation in here. So I'm just going to add some terms in here to this equation, basically, to this equation, and to that equation. And somehow these terms should be proportional to somehow with the magnetic charges. So let me do this addition. So these green terms, right, they were 0 before. Now I can add them like that. So basically they should be amount of the magnetic charges. So these magnetic charges are of course different from the electric charges. So for the electric charges, I have this electric charge and the corresponding electric charge current. These are the things that we are familiar with. Then if there are magnetic monopoles, then I can define magnetic charges for them. So somehow I'm going to define them, but let's just forget about how we might define them. But there should be a quantity that describes the amount of the magnetic charge in there. So I don't know. If there are 2 norths, for example, it's 2 units and things like that. And if these magnetic charges are moving, then in that case, there will be magnetic charge currents. So these will be entirely different currents, type of current. So they will also appear in there. So it appears that when you add these terms, the Maxwell's equations are still consistent. So the physics that's described by Maxwell's equations are still the same. So as a result, it is still plausible that the magnetic monopoles may exist. As a result, these equations may contain such terms. The nice thing about these is that actually these equations become highly symmetric. So let me actually highlight the electric charges and electric currents. So let's just repeat the argument in here. So for the electric flux, Gauss law for the electric flux, on the right hand side I have the electric charge. For the Gauss law for the magnetic flux, on the right hand side I have the magnetic charge. Right? So that basically expresses the fact that electric charges produce electric fields, magnetic charges produce magnetic fields. Simple enough. So that's basically where we have started with. And then there are the last two equations. These equations say, let's just repeat the arguments again. A time-dependent magnetic field produces an electric field. That's the first equation says. Time-dependent electric field produces a magnetic field. All right, these are already known. Now, in addition to that, I'll just talk about these currents. It just says that the electric current produces a magnetic field. That's Ampere's law. But the magnetic charge current would therefore produce an electric field, right? So as you can see, once you add these terms, it appears that the electric and magnetic fields are completely symmetric. So there are some additional differences between these equations. So there are these mu zeros, epsilon zeros appear in some places in here, but these are just artificial introductions that are introduced by our definitions of units. So if we just define, I don't know, the Coulomb unit for charge, electric charge, for example, or if I redefine the electric field unit, for example, or the definition of the Coulomb, basically, it is possible that I can eliminate this epsilon zero. And similarly, I can eliminate this mu zero. In that case, the equations become completely symmetric, and there are these plus and minus sign differences in here, but it appears that these are also consistent mathematically. There's no problem in here. So this kind of tells you that actually there's not much difference between an electric and magnetic field. So I'm imagining these kind of things like perhaps there's a parallel universe, an alternative universe where In that universe, there are no electric charges, so they have just magnetic charges. So their atoms are formed from magnetic charges, magnetic north and south charges, for example. In that case, these people will be searching for the electric charges, but probably they would call their magnetic charges as electric charges, and they will pose the same question as we are posing in here. In any case, we don't know basically, but this kind of tells you that it's a complete symmetry between electric and magnetic fields. So that's also one of the reasons why we don't distinguish electric and magnetic phenomena from each other. They are somehow interlinked with each other in a very complicated way. All right. So I'm just going to do a summary in here. So this is something that we already know. I have just repeated, but let's just do it again. So let's start with the Coulomb's law. So it basically says that an electric charge produces an electric field. So we just have an electric charge in here. It will just produce an electric field. That's Gauss' law. But if the electric charge is moving, if we have a moving electric charge, in that case it produces both an electric field and a magnetic field. All right, what happens for the case of a magnetic charge? So in that case, let's start with this. A magnetic charge produces a magnetic field, so that's what we are postulating. We are assuming that that's the case. But if the magnetic charge is moving, in that case, it would produce not only a magnetic field, which it normally produces, but it will also produce an electric field. So as a result, I mean, if someday we discover these magnetic charges, magnetic charge particles, magnetic monopoles, perhaps we can construct magnetic circuits in there. So in that case, there will be some magnetic charge currents which are flowing in that circuit. So there will therefore be magnetic currents. In that case, these magnetic currents would be producing electric fields around. So they are going to be electric fields around, right? So these electric field lines, of course, would be just like the magnetic field lines that we are familiar with. So they are just going to go around the circles. And perhaps we can even build some magnetic capacitors in here. So let me try to do it like that. Sorry about this. So perhaps there are these magnetic capacitors in here. So in which case we will have the magnetic charges collected in here on the plates. So the north charges in here and the south charges in here. And so as a result of that, there would be a magnetic field produced in here. I don't know. This is just a dream, of course. It's not a dream that cannot come true in near future, obviously. But this kind of a thing is still possible. But let's just repeat the main argument that I have said before. We don't know if the magnetic monopoles exist or not. So we just know that the laws of electromagnetism, all the laws of physics is consistent with it. But there are also some important clues. One of the clues is, I have also talked about this, is the quantization of the electric charge. Quantization of electric charge. We know that the electric charge in nature is an integer multiple of one fundamental unit of charge. So it cannot be anything else. So we know what that charge is. This is 1.6 times 10 to the minus 19 coulombs. In any case, we know that all the atoms, electrons, protons, all the composite particles, for example, have charges which are just integer multiples of that quantity. But we don't have any consistent way of explaining this. But somehow Dirac has shown that this is the case. He has shown that if there are some magnetic monopoles, in that case, he showed that it implies that the electric charge is quantized like that. So this is the most important clues. As a result, a lot of people believe that these magnetic monopoles do really exist, but probably we need to have very large energies to be able to produce them in, for example, collision experiments in CERN or something like that. Okay, So we don't know, but probably in the future, of course, we are going to have an answer about this interesting puzzle of nature.